Okay. Students, so you can better see it. Okay. So this is going to be the lecture for Lab 9 for Historical Geology. Students, bear with me. Hurting a little bit, so I will be doing my best to get through this carefully. All right. So what you're going to do first is you're going to open your lab manuals to Lab 9, which is on page 113. 113. All right. So on page 113, you will see absolute dating for historical geology. Absolute dating. So over the last couple weeks, we have discussed ways to figure out the age or approximate age of rock layers over time. So we talked about the relative dating, right? So we talked about relative dating. We looked at the various laws that go along with that. So we talked about the laws of superposition, the laws of cross-cutting relationships, and so on. Again, be prepared next week when you come into class, and we will discuss that again. But this week, we're going to look at more absolute methods to help date rock layers or help date material. Okay. So when we talk about something as relative, right? When we talk about something being relative, we talk about it being approximate. So we know that the rock layers that we were looking at, we know the approximate age. Remember, we talked about the KT boundary. And the KT boundary is one that you're going to have to know when it comes to your test. I'm going to ask you about this. And the KT boundary is the boundary between the Cretaceous period, which was the last period where the dinosaurs reigned over the Earth, and the beginning of the Tertiary, which marked the rise of mammals. But that KT boundary is a way for us to show that is almost a universal marker that we can find around the world to help us figure out the date of the rocks. But because we only know the relative date, we cannot figure out the exact time, day of the week, and which year exactly that the KT boundary was formed or that the meteor impacted our planet. So with that in mind, we're going to get into some methods today that talk about ways that we can more exactly date material. Okay, so the first thing we're going to do, I'd like you to turn on your lab manual to page 114. Page 114, we're going to discuss ways that we have attempted to date material, but hasn't quite worked. There are multiple ways for us to do this. So originally, and I have it here on the board, originally scientists had tried to look at deposition rates. So you remember that when we talked about sedimentary rocks, so deposition is one of the ways in which the sedimentary process occurs, right? So when something is deposited, it cements or compacts, okay? You remember this from our sedimentary rock lab. And the deposition rates are something that scientists looked at in an attempt to try and figure out just how old certain areas were. But there was a problem with this. As with many things, remember talking about plate tectonics as well, geologic processes aren't constant. They aren't constant. So trying to figure out deposition rates of rocks over time could yield you some fairly accurate results in the short term, but over time, we don't know what processes took place before that for those layers to form, right? So that didn't work. And we're cross that. So deposition rates, no, didn't work. Okay, so another way that we attempted to figure out certain ages of things. This one in particular, ocean salinity, we were trying to figure out the age of the oceans by figuring out just how much salinity or material, salt material, was in the water, was in ocean water. And this is where they talked about transportation. Again, remember, we're getting into a sedimentary process here. The transportation of material, and scientists believed that if they could figure out the volume of salt in our oceans, then they could figure out the age of our oceans by determining the rate of which they had salt added to them. But again, remember that there are no processes that are exactly constant, right? So that didn't work. Ocean slowly didn't work. Okay, now we have Lord Kelvin. Lord Kelvin. We're going to do a little bit of history here, class. So Lord Kelvin was a British scientist who, I say scientist, perhaps maybe science enthusiast, but he had tried to take the cooling of the Earth. He tried to look at the cooling of the Earth and assumed that the rate at which the Earth cooled was constant, right? So he had two things that were wrong with his assumption, two issues. One, he assumed that the Earth was molten from the very start. He assumed that was the case from the very start, that the Earth was completely molten at one point. That is not the case. That is not the case. We do know that we talked about the Hadean period, right? Harkening back to the first lesson. The Hadean period was a very hot, hellish period in which was marked by volcanoes and outgassing, and we didn't have a proper atmosphere, and this was the point where the volcanoes were spewing gases into the air and helping to create the precursor to the atmosphere that we have now. So Lord Kelvin didn't quite have it right because he assumed that we were molten. But even with this assumption, he got close. He got close, but even trying to do this by looking at the rate, the cooling rate of the Earth, which we are constantly cooling. We are constantly throwing heat back out into space. But he did not get it right. So if we can't determine the date of our planet or the date of a rock through its deposition rate, or maybe looking at the ocean, its salinity, or looking at its cooling, how can we do this? Well, I have an answer for you, and we get into radioactive dating. Radioactive dating. I will tell you that there comes a point where material here on Earth has constantly been recycled over time. You remember we talked about plate tectonics and how the plates are constantly moving, right? And you have plates that, again, remember we talked about, so your divergent boundaries, right? So your divergent boundaries are pulling apart and creating new material, right? Your convergent boundaries are converging onto one another. So remember, again, one plate goes beneath another, the plate melts, right? And new material is created. And then you have your transform boundaries, okay? We talked about those. But remember that we are constantly creating new crust. So there comes a point where we can only date back so far because we only have so much crust to work with before it is constantly recycled and changed. Although there is some very old crust that exists in certain places on Earth. There's some places in Canada that have crust that is 2 billion years old. It is ultramafic. Remember, again, we talked about the mafic material, high in iron, right? And therefore dark in color. So ultramafic that we know is extremely old. But okay, I'm digressing. Let's get back to relative dating. So go to page 115. Page 115 for radioactive dating. Sorry, I misspoke. So page 115, we have radioactive dating. And I am sure that you have heard of the term half-life, a half-life. So if you've part of video game circles, you know what this is. So half-life is looking at the decay of radioactivity in an element, right? So as you can see here, your lab manual discusses, and we're going to go over this very briefly because I also want you to read this as you're doing this. Be sure to give the lab a good read before we continue because I'm giving you a very a good overview. But again, I want you to understand the material a little bit more deeply here. Okay, so we have neutrons, right? They have an atomic mass, but they are neutral. Okay, and we have protons that have an atomic mass but have a positive charge. Right? Then we have the electrons, which essentially have no mass and a negative charge, and are usually present in numbers equal to the number of positively charged protons. Okay, so what we can do is we can chart the decay of these elements over time. And if you look at page 116, we start talking about, so C14, carbon 14 is something that is present in almost every living thing. So let's say, for instance, we find the body of a pharaoh in a tomb, right? Or maybe a caveman frozen in ice. Well, what can we do? How can we figure out how old that is? Well, what we can do over time is we can look at the amount of decay that has occurred on that body and see how many half-lives, how much material is left, okay, in those molecules, in those atoms. So, sorry again, I'm not a chemist. I want to preface this, I'm not a chemist. So I am presenting the material as it is here. So again, as I've mentioned before, in science there are always exceptions, but for the purpose of our labs, just stick with what we got here. So when you look at half-life, right, you can have multiple half-lives, but you're looking at the percentage of parent material versus the percentage of product that is remaining. I think in the book it calls it the daughter product. Okay. So over time, and every material has a different half-life, but we're looking at carbon 14 right now. Okay, looking at C14. And the graphs on page 116 and page 117, okay, 116 and 117 are going to be the graphs that you are going to use for the rest of the lab. We're actually almost pretty much done with the lecture here. I'm about done preaching to you about the stuff that we have to do. But you will read through the lab. Give the lab a good read. I have given you a good overview of the important material. Remember, if something goes on the board, it's important. If something goes on the board, I'm not going to put something up here. I'm not going to waste your time and mine by writing something up here that doesn't matter. I am probably going to ask you on the test to give me at least one of the ways that we have tried to absolute date something that didn't work. Because science is not just about its successes, it's about its failures. So I'm going to want you to know at least one of the ways that we've attempted to do this. How in the past have we tried to absolute date something? And as you can see, we have, again, the deposition rates, right, through the sedimentary processes, okay? The ocean salinity, again, through the sedimentary process of transportation. And Lord Kelvin's method of looking at the cooling rate of the Earth. Okay, so looking ahead in your lab, it would behoove you to do the practice. And the practice begins on page 119. And there are a few practice problems. I'm going to say this. If you do the practice problems and you send me a picture of them, send me a picture of your practice problems, I will give you some extra credit on the lab. Please do them. Please do them. I will give you some extra credit on the lab if you do the practice problems. Okay? I will tell you that I will grade very lightly. I will grade very lightly because I want to see that you are understanding the concept, or at least attempting to understand the concept. For the lab itself, you might look at that and go, wow, that looks crazy. Listen, take it a step at a time. Go with the questions and ask. I'll ask you what the oldest rock is. So remember how we did the layers, right? And again, be sure to pay attention to the various laws that we had there, the law of superposition, cross-cutting relationships, horizontality, and so on. So keep that in mind. You're kind of taking everything that we've learned so far and putting it into this lab. And this will be the last, I think, quote-unquote dating lab. Next week, we're going to get into fossils. So this lab, students, is going to be due on Wednesday, the day before your next class period. I understand we didn't have class today. Thank you for being patient with me. But I'm going to give you 6 days with which to do that. So please do that. Watch this video and do that. I will post this video on Canvas. If you watch the video, tell me in the comments on Canvas that you've seen it. I'll give you a bonus point. So, okay. So if you have any questions, feel free to email me. I will put my email on the notification. And good luck. Be sure to read the lab.